Yeah, I'm like the total opposite of you today. My daughter did not want to get out of bed this morning, and so I was like, okay, then I'm not gonna, then don't get out of bed. So I don't know what happened. I left. So I didn't have to drive in traffic today. It was awesome. It was so great. I'm like in such a great mood today. Yeah.
So now she's been staying up late, and then when I wake her up, she gets up the first time.
Yeah.
She's not the nicest person,
but
she's
yeah.
and I'm very happy.
Yeah, well, I tried 3 times, and we had to leave, we only had 10 minutes left.
Yeah.
So I was like, there's no way it's happening, so. But my wife was there, so I said, go figure it out with Mom. So, yeah, I woke my wife up. Said, hey, she's asleep upstairs, have fun. So, yeah, I know.
Although I'm not gonna lie, I do not miss the days where they woke up.
Yeah, you're telling them to go back to bed. Come on. Come on. All right, we should get started, yeah? It's 9 o'clock, so you could potentially have 3 things for me today, right? 3 things? I don't know how I want you to hand these in. Let's do this. No one sits there? Okay, let's do this. So you have the test corrections, if you did those. Well, that's a quiz grade, right? And then you have the quiz that I put on the board, and then you have an optional bonus. So let's do it. Let's do that right here. 3 piles. So, pardon? I would like, if you're doing test corrections, I would like to see the test as well, because I want to be able to see what you did on the test and compare it. If you don't have that with you, then just turn in your corrections at least. So let's see, it'll be corrections, and then this is quiz, and then this is bonus. Corrections, quiz, bonus. Corrections, quiz, bonus. All right, we have a lot to do today, all right? We're still in chapter 7, section 2. There's a lot more to this section. So I want to make sure before we proceed that everybody is absolutely clear on the picture of what we're doing, right? And there's something I want to point out that we're going to need here today that I don't stress as much when we're setting this all up. I think it's obvious, but I will point it out anyway. So what we've been doing, at least last time, is we had some function of x, another function of x, the region between them, and we're now rotating this around some, horizontal line. And so we have this method of washers, right? And the integral for this, right, is pi integral from A to B. A to B are where the region starts and stops. Yes? The A and B is where the region starts and stops. A and B are restrictions on x, right? The x values. All right. Then we have what we said, R out, whatever that is, squared minus R in squared. And then this integral will be with respect to x, right? The thing I want to point out is this, that the distance from the y-axis, all right, from here to our rectangle is always x. And the way to think about it is that the integral tells you where x is going to start and stop, right? So this rectangle is going to start, right? The x value of the rectangle is going to start at A, and then it's going to push through to B, right? That'll be important for us, right? Also, the other thing I want to point out, and I think this is the part that's obvious, the distance from the x-axis to this function f is the value of f, right? That distance is always f. This distance is always g. Now, r out, that distance is not always f. It depends on where this line is. If this line is the x-axis, then of course that distance r out is f of x, and r in would be g of x. Are there any questions on that picture? Sure? Okay, so this was the quiz problem, right? This was the quiz problem. You were asked to take this region and to wrap this thing around a few axes. Did that go okay? Feel all right with it? Wondering, should we do it? Is it worth our time? We'll do one of them. How about we do one of them? Because there was 3 different lines to wrap it around, right? Which one do you want me to go around? Do you remember them?
I think the -3.
Okay, y equals -3? Let's do that one. Okay. Was it -3? It was? Yeah, and then the other one was 4, right? Wasn't it? Okay, so if we want to do, it was y equals square root of x, y equals 1 over x, and x equals 3. We want to wrap that about the line y equals -3. All right, so I'm just kind of throwing this up here real fast. So you have that picture, right? Y equals -3. I'm going to go ahead and graph that. I'm going to have to zoom out. There it is. I'll make it dotted in orange. How about that? So we are trying to wrap that region around that dotted line there, right? So quick sketch of that, real quick. We got our region. There's our region. We've got our axis of rotation right here. And here's our rectangle, right? The top function, right? The top function here, this one, is the square root, right? That's the square root of x. And the bottom one is the 1 over x. We're going to start at x equals, I guess you had to find their intersection, right? And you could do that by probably just inspection, right? Just by looking. It was 1. And then the 3 comes from the vertical line that you're given, right? And so let's find r out, right? R out would be distance from here all the way down here, r out. R in is a distance from here all the way to here, r in. So r out will be this distance, which is how much? 3. And you're looking at it as absolute value. Don't look at it as -3. So 3, and then from here to here would be the root x. So r out would be however you want to write it, root x plus 3 or 3 plus root x, doesn't matter. And then r in would be similar to that. It would be this 3 plus this much, which would be the 1 over x plus 3. And then you just crank this into the formula. So pi integral 1 to 3. We start at 1, end at 3. it's r out squared minus r in squared, all of that dx. And I did not want you to evaluate these. I hope you didn't. If you did, you wasted a lot of time. It was just the setup, so that's all I wanted right there was this. Be careful. Remember, like, you can't just like square each one of those, right? You can't just turn this into like x plus 9. You would have to FOIL. I'm not even asking you to do that, but don't do that and make a mistake and then I have to take points off, you know, because you did something wrong algebraically. Does that help? Yeah. Good? Okay. The other answers, just so we know, would be the same thing. The one where you go around the x-axis, this 3 would be gone. And then the other one where it was y equals 4 above it, this one would have been 4 minus 1 over x squared. And then the other one is 4 minus root x. They change positions, what's r out and what's r in, because if the line's up here, the distance from here to here is r out, right? From here to here is r out. And so you're working off of the red function, not the blue one. So, all right. Now, the next thing we need to look at, you have your the sheets I gave you last time, right? The color handout. Okay, that color handout, the very first section of this, right? We're doing method of washers. We're saying that the rectangle that we draw is orthogonal or perpendicular to our axis of rotation. But in this first section, we are looking at two functions of x, right? Two functions of x. If you scroll down a little bit, or if I scroll down, you look down, right? You see here that we have another sort of scenario where we have two functions of y instead of two functions of x, right? So when we have two functions of y, and we want to rotate around a vertical line. So if we have two functions of y, we draw horizontal rectangles instead of vertical. And we want to rotate around a vertical line. Notice that the rectangle is perpendicular to the axis of rotation. We are then going to use washers, right? It's the same sort of concept, but this is what you do when you have functions of y. So the setup is exactly the same. You're going to imagine wrapping these rectangles around that vertical line. It'll create a washer. You need to figure out the r out and the r in. But instead of, you know how r out over here was like from here to the top or here to the bottom for r in? Because everything's sideways, it's going to be like r out's going to be going this way and r in's going to be this way. So everything's just turned over on its side, basically. And so our formula is pretty much the same thing. Pi times, now the integral is going to go from c to d instead, right? Instead of a and b left and right, we're going to say c and d, that's up and down. And it'll still be r out squared minus r in squared, but now our integral will be with respect to y because both of our functions are functions of y, not x. Does that seem like a pretty clean transition into this? So I have an example for us to do. Wait a minute, I think I typed it up. Where is it? Where did I put it? I have a bunch of things open right now. Hold on. I think it's this one. Yes, this is it. I'll make it bigger. I'll let you read that for a second. All right, got it? You have to rotate, find the volume of a solid formed when you rotate the region bounded by x equals y squared. X equals, that didn't come out too good. It's supposed to be sine of pi over 2y. That region, we're going to rotate it around three different things. So we have to draw it first, right? We have to draw that region. We have a couple of options. Desmos, right? But that doesn't help us on a test. I'll show you what Desmos does. Okay, there's the graph from Desmos. And I already got the region for you. You see that? But I also have it on the calculator. So I'm going to bring up the calculator. Hopefully it remembered what I typed in. Yeah, it's still there. Great, awesome. So let me show you what I did. I went to parametric mode, right? I went to parametric mode on my calculator. And because these are both functions of y, right? Because they're solved for x, they're functions of y. I'm using parametric mode. For the first one, for this one, I let my x be t squared, I let my y be t. And then for the other one, I let my x be sine of pi t over 2, and I let my y be t. We've gone through this, right? Like, I don't need to, okay? So then when you graph that, and I had to zoom. I had to change my zoom. I had to like zoom in a little bit to make it look good, but that's it right there. So that's my picture, okay? So I'm going to go off that picture, and let's do part A. Part A, I'm supposed to rotate this around the y-axis, which is the same as saying x equals 0, right? That's the same thing. So here's my drawing. There's my y-axis. Here's my x-axis. I have two functions. I have the sine of y, this one like this. And then the other one is the y squared, that's this one like this. So you have to know which is which, right? This is x equals sine of, I said y, sorry, pi over 2y. And then this one, bless you, is x equals y squared. From the look of it, from the look of that region, could we do vertical rectangles?
Yes.
It looks like we could, but the problem is we'd have to solve both of these for y, right? I'd have to solve that for y, which wouldn't be such a big deal to solve that for y, just square root of both sides. But this one, I would have to bring in an inverse trig function, right? Inverse sine on both sides. I don't want to mess with that. So I'm just going to say, well, even if we did, okay, let's say, even if we made this a vertical rectangle, what would be the problem? We're rotating it around a line that goes vertical as well, right? The rectangle and the line of axis of rotation are both parallel, right? Washers is what we use when they are perpendicular to one another. So our washers wouldn't even work if we were to switch it to a function, these to functions of x. So I'm kind of forced in this scenario to say, okay, I'm going to draw a horizontal rectangle like this, right? And they're going to go, start at the bottom and move up through this region. My axis of rotation, I brought a purple today. My axis of rotation is actually the y-axis, right? It's my axis of rotation. Let's see, I'm kind of like all over the place here. What do we want to do? Do we want to find where these hit each other right now or deal with that later? Totally up to us. Do it later, right? So we're all going to do something different, right? Since I brought it up, can we just figure it out maybe without much thought? Like this one looks pretty obvious, doesn't it? 0. And just check. I mean, if you plug 0 into this, right, we're plugging in 0 for y, right? For y. If we plug in 0 for y, what's sine of 0? 0. And then if we plug in 0 here, we get 0 as well. So 0 works, right? So that's 0. So if I'm thinking about the integral, I already know that my integral is going to start at 0. I know I'm going to have a pi out here. Where does it stop? I need the y coordinate, right? Not the x. I need the y coordinate of their intersection. And for this, I thought that maybe you could do it by inspection. I made it nice. I made it something obvious, like that you would think. 1. 1 works. 1 works. Why? Well, what's 1 squared? 1. Okay, what happens if I plug in 1 here? You get pi over 2. What's sine of pi over 2? 1. Okay, they're the same. So this is 1. On any exam, I would make sure that it's something nice. I wouldn't make it like crazy. It would be some obvious number. Okay, so that's 1. So now I know my integral stops at 1, right? All right, now I need to figure out RO, R out, R in, right? So if I'm standing on the axis of rotation, looking out at my rectangle, R out is going to be the distance from the axis of rotation to the outer edge of the rectangle. That's R out. And R in is going to be from the axis of rotation to the inner edge. Can you all tell me what this distance is from here to the blue? It's just that function, right? It's just that function, sine of y squared. Or sorry, why did I say that? R out is sine of pi over 2, y. Right? That's what R out is. And then R in is just the distance from here to here, which is the red, isn't it? And that's just y squared. And now I just plug into the formula, and I'm pretty much done. So I'm going to say it's the R out, right? All of that squared. Is it all right if I just put the squared on the sign then? That's the same thing, right? That means the same thing as squaring it? Okay, and then minus now this one squared. That'll be y to the 4th, won't it? But I'll put y squared squared. Was there a question? dy. And then whatever, we could evaluate that integral. Well, we wouldn't evaluate that. We go to a computer and evaluate that. Could we though? Could we do it? Do you know how to integrate sine squared? How do you integrate sine squared? Yeah, half angle, like power reducing, right? Turn that into 1/2, 1 minus cosine 2 theta, that thing, right? Okay, so we could do it. All right, we're done, yes? Now let's move on to the next part, part B. So for part B, I'm asking for you to rotate it around x equals -1. Now look, on your exam, I told you, I'm not going to require you to evaluate these integrals, right? You don't have to evaluate them, just set them up. But I do expect you to draw me pictures for each of the 3 scenarios, or however many scenarios I give you. They don't have to be like perfect pictures, but take a moment, you know, to get something decent on paper here. Okay. So it's the same sort of picture. We have x equals y squared. We have x equals sine of pi over 2y. We have our axis of rotation is now back here at x is -1. And then our rectangle, again, is going to be horizontal. We already know that this is 1 up here. We already know that that's 0, right? So now our R out is really what I need to figure out, is now the distance from the axis of rotation all the way to the outer edge. And our R in is the distance from the axis of rotation to the inner edge, right? So how has R out changed now? Remember, from the y-axis to here, right, that was sine of pi over 2y, right? But now we have to add to that this distance, which is 1. So R out will be, however you want to write it, sine of pi over 2y, right, plus 1. And then R in, same thing. It'll be the bottom one, the red one, which is y squared, but then plus 1. And then you just go into the formula. You take those quantities and square each one, subtract, and we're done. So pi, integral, 0 to 1. Okay, r out, sine pi over 2y plus 1, that entire quantity squared. This time you can't put the squared on the sign because you have to square the whole quantity. So you have to have it like that. Then minus, now y squared plus 1, that quantity squared, the entire thing with respect to y, and we're done. Yes?
So if the variable that the axis is changing, if it's always negative, is it always going to be that you're going to add it to the equations that are given, and then when it's positive, it goes out front, and then you subtract the equations that it gives you? I'm sorry if that sounds.
No, I'm seeing if I can answer that question with a yes. I can't, because that depends on where the region is. So all the examples that I give you in class are in the first quadrant. And the reason I do that is keep it simple, right? But let me just kind of give you a visual of something where that wouldn't work, what you're suggesting, all right? So what if we had this scenario where you had your region is over here, okay? Let's say your region's over here instead. Like that, okay? And now your axis of rotation is to the right of it. So say your axis of rotation is 3. Are you going to subtract those values? You know what I mean? Like, see, you're adding this time because the distance is this plus that. So I think you have to look at it, like I said last class, don't try and make like a general, do this when you see that, like, just work out the geometry, look at the distances, see what they are, right? And then create your formula. Does that make sense? All right, last one, x is 2. So for this one, I'll go real fast. Done. Did y'all see all that? It's finished. I already erased it. No? X is 2. So x is 2. Now in this case, I think it will do what you're suggesting because of where it's placed. So we have our sine. I'm not even going to write that that's the sine one. This is the y squared one, right? Our rectangle's in here. Our axis of rotation is now x equals 2, which is over here, right? So this time our r out is the distance from the axis of rotation to here. So this, from here to here, r out. From here to here, r in. Right? That's different now, right? From the axis of rotation to the outer edge, axis of rotation to the inner edge. All right, r out for us is, yeah, you have to know what this whole distance is from here to here first, right? That's 2. And this time, it's not all of 2, right? You have to take away this much. Well, this much is the red function, so it's 2 minus y squared. Okay, and then this Rn, similar idea, is the whole 2, but we take away this much, right? So we want to know that distance. It's this whole distance 2 minus this much, but the blue one is the sine one. So 2 take away sine pi over 2y. Questions there? Are y'all finding this whole topic easier or than compared to like the techniques of integration, partial fraction decomposition? Because it's visual, I think it's a little bit easier to catch on to. But every time I've ever said that, I always have students that will be like, well, no, this doesn't work for me. So it's different for every student, but generally speaking, students do better with this. So it's the same limits of integration. We still have a pi out front. It's r out 2 minus y squared. It's that quantity squared minus the r in squared 2 minus sine pi over 2y, that quantity squared, and then all of that dy, whatever that integral is. And that would be the volume of the solid if you were to wrap that thing around the line x equals 2. All right, I think we're done with washers. Okay. So what I'd like to do now is I'd like to go back to the quiz question. Okay? Let's go back to the quiz question that you turn in. Oh, if you have that, please, if anyone turn in, I've collected already. Test corrections, the quiz, and the bonus. All right, the quiz question, I gave you y equals square root of x. I gave you y equals 1 over x. I gave you x equals 3, right? And I asked you to wrap these around horizontal lines, didn't I? Horizontal, the x-axis, then a line that was below it and a line that was above it. This time, what I want us to do is I want to rotate this about these 3 lines. The y-axis, x equals -2, and x equals 5. This is different. This is different. Because if you go to your region, right, I'm going to just draw it again because we already had it up there earlier. Went like this. Well, that's a little bit too much. It went like this, and then like this, and then like this. Okay, I had the region up there earlier. This was, oh geez, this was square root of x on top. This was 1 over x on the bottom. So what we did before, right, for the quiz is we had vertical rectangles, and we rotated them around lines that were horizontal, so our rectangle was perpendicular to our axis of rotation. Here, if I want you to rotate around these, do you all see these are vertical lines? We have a line that, you know, the y-axis is this, x equals -2 is this, x equals 5 is this. We want to rotate around those. So we have a couple of questions. First question is, does it even like look the same? Does the solid even look the same as when you rotate it this way? Well, let's resolve that first. So here I want to go back to what I showed you last class. This one? Yeah. Okay, so this is kind of what we started with last class, right? I gave you this picture. I said, hey, we're trying to find the area. Take that rectangle, and let's pop that into 3-dimensional space, and then let's wrap that thing around the x-axis, right? And I said, oh, if we do that and we just get all of them and sum them up, we will get that solid shape right there, right? And we can find the volume of that. Happy? Understood, right? Let's back it up. Now, instead of wrapping this thing around the x-axis, what would happen if you wrap it around, like, let's say the y-axis? Do you see you get a completely different shape than the washer? Do y'all see it rotate around the y-axis there instead of around the x? That's a completely different shape. And if let me take the washer out of here because it's just distracting us now. If I vary my x through this region, see how those things change? All those things change shape, like that. If I were to put all of those together, I would get this solid. That's what it would look like.